Now we want to talk about, where do these electrons live? Where do they live in an atom? And so if you look at a picture like this, so this is a probability density map, and think about it as like taking a bunch of pictures. You have an electron. Electrons are not stagnant. They're constantly moving, right? And so if you took a bunch of pictures of an electron and you kind of superimpose them onto the same spot, and you can see, where the electron likes to hang around. Where does it like to visit? And so the darker spots there mean the electron was there a lot. I took a lot of pictures and the electron hangs out there a lot. And then where it's lighter, it means they don't. So you can see that this particular electron kind of likes to hang out in this spherical region. So it's kind of like a sphere. This is an s orbital. And so we're gonna use something called quantum mechanics. Not a lot. We're gonna in name only. We're not gonna do any of the math to kind of explain, to try to figure out like where do the electrons hang out? How can we describe these orbitals? So this is an orbital. And we want to look at a couple things. We want to look at the energy of the orbital. Is it low energy or higher energy? Is it energy level 1, 2, 3? Where's it going to go? Is it a sphere? Is it a dumbbell? What's the shape of the orbital? And then what's its orientation in space? Is it along the x-axis? Is it along the y-axis? So an orbital like this is an s orbital. It's just centered kind of right in the middle. There's no really other orientation. It's just right there on the origin. So quantum mechanics uses a wave equation, which you know what waves are. If you have sines and cosines, you basically put all the stuff together. You can square that wave equation, and then that's how you get this probability density map. You don't really have to worry about that so much. But this quantum mechanics is based on this particle wave duality of matter. And the main guy here is Schrodinger. So how do we describe these electrons? We're going to use, or where the electrons live, these orbitals. We're going to use quantum numbers to help us do that. So an orbital, again, it's just kind of describing where does the electron live. We're going to look at the energy, the shape, and its orientation in space. So the first quantum number we want to look at is called the principal quantum number, or n. And that's going to tell us what energy level the electron is. N starts at 1. Starts at energy level 1. So n can only be 1 or greater. It can't be 0. You can't have negative numbers for n. N is 1 and on. And if you have n of 1, you're in a low energy level. 2 is greater. 3, the bigger the n gets, the higher in energy you are. So think about energy levels as like if you had this picture of the atom in your head, right? This is the nucleus. This is energy level 1. This is this is 1. This is 2. 3 would be over there, and so on, and then 4 would be over here. So the further away you get from the nucleus, the higher energy orbital you're in. Okay, so that's n. Angular momentum quantum number, that's L. That describes the shape of the orbital. And so if L, and it starts at 0 and it goes all the way up to n minus 1. So L is directly related to n. So if n is equal to 1, L can be 0 all the way up to n minus 1. So if n is 1, then L can only be 0, right? If n is equal to 2, then L can be 0 or 1. If n is equal to 3, L can be 0, 1, or 2, right? It goes all the way up to n minus 1. So L depends on n. How many L's you have depends on n. So how many different shapes you have, it depends on the energy level you're in. Think about it that way. So what do these different L's really mean? So if L is equal to 0, you have an s orbital, right? And it's just spherical. If L is equal to 1, you have a p orbital, and p orbitals are dumbbell shape. If L equals 2, you have a d orbital, and that's like this. So S is a sphere, P is like a peanut, D is a daisy. L equals 3, it's called an F orbital. I'm not going to draw it. It's all kinds of crazy. I don't know. They're nuts. So really, you should be able to draw S, P, and D orbitals. So again, energy level, the first quantum number tells you about the energy. The second quantum number tells you about the shape. Is it an s orbital? Is it a p orbital? Is it a d orbital? F orbital? What does the shape look like? S's are always spherical. P's always look like a peanut. D looks like a dumbbell. And then the third one has to do with the orientation in space. So think about this p orbital, right? If I have x, y, z coordinates, I can have a p orbital going here, I can have a p orbital there, I can have a p orbital on the other. I have 3 different ways to orient that p orbital on each one of the axes. For a d orbital, I have 5 different ways. An f orbital, I have 7 different ways. So I'm going to scroll down here just for a second so you can see what I mean. So an s orbital, there's really only one orientation. For a p orbital, you can have it on the z-axis, the x-axis, the y-axis. Those are different orientations in space. So I have 3 different p orbitals because I can orient them 3 different ways. And these are all your, 3 different p orbitals, yep. And then I have 5 different d orbitals. And these are some of these are on the axes, some are between the axes. It's weird dz squared. And then F, there are 7 of those. So you have different orientations in space. That's the last quantum number. So for describing orbitals. So you have the first one tells you about the energy level. You know, are you over here? Are you energy 1, 2, 3? Energy level 1, 2, 3. L tells you about the shape, and it's related to n, right? So if n equals 1, then L has to be 0. If you're an energy level 2, you can have an s or a p orbital. If you're an energy level 3, you can have an s, p, or d orbital. And the third quantum number, right, tells you about the orientation in space. And this is going to range from negative L all the way up through 0 to positive L. Whoop, positive L. There we go. So if L is equal to 1, then ML can be equal to negative 1, 0, or 1. Or if L is equal to 2, ML can be negative 2, negative 1, 0, 1, or 2. So we're going to practice coming up with all of these quantum numbers. But so here, if I have ML equals negative 1, 0, or 1, I have 3 different orientations of p orbital, which makes sense. And for L equals 2, I have a d orbital. I have 1, 2, 3, 4, 5 different orientations because I have 5 different ways to orient them in space. So here you can see again, this is ML negative 1, ML 0, ML positive 1, or over here you have negative 2, negative 1, 0, 1, or 2. So you really you're not really assigning each one of those ML values to a particular orientation. It's just counting the number that are possible. Oh, I'm getting dizzy. Okay, so on any energy level, you can always have, there can be up to 1 s orbital, 3 p orbitals, 5 d orbitals, or 7 f orbitals. That has to do, again, with the ML quantum number. A shell, if you're talking about a shell is basically orbitals that have the same value of n, and subshells are a particular type. So I can have a p orbital, or I can have like a sum of all my orbitals in that energy level. So in energy level 2, I can have s orbitals and p orbitals. That's my shell. The subshell would be the s or the p orbital. The shell is all of them. So let's work through this exercise here where we try to list all the quantum numbers that we can have for different energy levels. So if n equals 1, right, n equals 1, n always starts at 1 and goes up to whatever, 1, 2, 3, 4, 5. L is always going to go from 0 all the way up to n minus 1. So if n equals 1, L is 0, and then 1 minus 1 is 0, so I only have one possibility. And so, right, my subshell designation has to do with the first 2 quantum numbers. So if I'm in energy level 1, I have a 1 here. My subshell designation is 1. And then since L is 0, I have an s orbital, right? Remember, because if L is 0, I have an s orbital. If L equals 1, it's P. L equals 2, it's D. L equals 3, it's F. S, P, D, F, yep. So that's what we're talking about here. So it's N, and then L. My ML values are always from negative L through 0 all the way up to positive L. So if L is 0, ML is 0. So I only have one orbital in my subshell. So 1s orbital right in the subshell. So I have 1 total orbital there. Let's try another one. So 2. So if n equals 2, L could be 0. It could be 1, right? Because if n is 2, then 2 minus 1 is 1. Which means I have over here 2s orbital, and I have a 2p orbital. So remember, this L value 0. If L is 0, I have an s orbital. If L is 1, I have a p orbital. For ML, take this first row. For ML, if L is 0, then ML is 0. If L is 1, ML could be negative 1, 0, or 1. So in this subshell, I have 1 orientation, right? I just have s orbitals. And then in this subshell, right, in the p subshell, I have 3. So 3 plus 1 gives me 4 total in that shell. So in that shell, I have 4 orbitals. Let's try 3. 3, if n is 3, L could be 0, 1, or 2, which means I have a 3. All these are in the third subshell. So I have 3S, 3P, or 3D, right? That SPD comes from the L. If L is 0, it's an S. If L is 1, it's a P. If L is 2, it's a D, and so on. If ML is 0, if L is 0, ML is 0. Then I have -1, 0, 1. Now I have -2, -1, 0, 1, or 2. I have 1 in this energy level. So this subshell, I have 3, and now I have 5. I'm just counting up how many numbers I put there, and then I add all these up. 5 plus 3 plus 1 is 9. This number over here is always going to be n squared, right? So if I'm an energy level 1, 1 squared is 1. If I'm an energy level 2, 2 squared is 4. If I'm an energy level 3, 3 squared is 9. You can do the same thing for 4. I think I'm running out of time. I can have 0, 1, 2, or 3. So here I would have, 4S, 4P, 4D, 4F, 0, -1, 0, 1, -2, -1, 0, 1, 2, and then -3, -2, -1, 0, 1, 2, or 3. So this is 1, 3, 5, and 7. And then since I'm an energy level 4, I have 16 orbitals. So you can go through that chart again and then try to work on the next problem.